prove now our theorem 5, which says just that we take two sets, x1 and x2, non-empty and convex, no further assumptions, just non-empty and convex, and the intersection empty. No closeness, no boundedness, nothing. And then there is a separation hyperplane. Okay. Again, no strict or strong or something like this, just separation hyperplane. There is a separation hyperplane. The proof is as follows. We take this x1 and x2, which are convex, and consider capital X as a difference of them, x1 minus x2. And this is also convex. We discussed that sum or difference, the same of convex sets is convex. Okay. Now, this is what we know. And we know also that 0 is not, okay, we know that x1 and x2 intersected are empty, and therefore, if we consider the difference of them, then 0 is not element of it. Yes, 0 is not element of x, which is x1 minus x2. Okay. 0 is not element of x. And of course, therefore, it is also not an element of interior of x for sure. Now they are in the situation x is convex, of course non-empty, and just x convex non-empty, and 0 is not an element of interior of x, and this is exactly what we can apply our theorem for. Yes, our theorem 4 was exactly the situation. They have a set, and they have a point not in the interior, and then there is a separation plane. Yes, and therefore what we know now by theorem 4, there is a separation plane HAB, which separates this x, which is x1 minus x2, and 0. And now it remains to prove that this separation plane also separates x1 and x2. How to see this? Okay, what we have. If this hyperplane, yes, hyperplane, if this hyperplane separates x minus x2, x1 minus x2 and 0, what does it mean? It means that A transposed, okay, what does it mean? It means that, okay, vector A is a vector in Rn, B is a number, and let's say X is subset of H less or equal AB, and Y is an element of H larger equal AB. Okay, this means the separation, or more precisely, it means that A transposed times an element from capital X, and what is every element from capital X is some x1 minus x2. Yes, x1 minus x2 is less or equal than B for all x1 in x1 and x2 in x2, and at the same time A transposed 0, okay, not Y, it's just 0. Yes, our element is 0. A transpose 0 is larger or equal than B. Therefore, B is less or equal than 0. Okay. Okay. This is what we have. Do you agree? Is it clear?
when we proved separation between two sets with additional assumptions, we also used similar construction, right? We proved separation between x1 minus x2 and 0.
Exactly, it's the same logic of the proof, but now the difference is that there the used a theorem which requires closeness of x, and it was certain difficulty to prove closeness of this difference. And we have seen that if x1 and x2 both are closed, this does not in general imply the closeness of the difference. And therefore, there we required boundedness of one of the sets, and with this we had also closeness of x. Here, since they are already in the situation there, we removed the assumption of closeness, it is easier to go through this proof. Yes, it is easier to do this logic, since now they have here convexity, and for difference they also just need convexity. They do not need anything else, and therefore they can apply directly the Praeder's theorem. Okay, but the logic of the proof is similar. Do you agree?
Yes.
Okay, now they have this, and now how to see that they have now a separation of x1 and x2. This was the similar logic as they had in the theorem you mentioned. They have from this that A transposed x1 is less or equal than A transposed x2 plus B. And since B is for all x1 from x1 and x2 from x2, and since B is less or equal than 0, you can just say that, okay, A transpose x1 is less or equal than A transpose x2. Yes, this is less or equal than 0, and therefore this guy is less or equal than just this. Okay, we have this for all x1 and x2 from x2. Okay, do you agree?
Yes.
Okay. And now from this we can say that, okay, if we consider the set of all numbers at x1 for x1 in capital X1, this set is bounded from above. Yes, since, okay, we just take one element of from x2, and they have here bound for all such inner products A with x1. Therefore, this set is bounded from above. And for the same logic, A2 x2 for x2 in capital X2 is bounded from below. Therefore, there is a supremum of this set and there is an infimum of this set. And we can take, let's say, constant C just as the supremum of A transposed x1. X1 is capital X1. And this will be for sure less or equal than infimum of all A2 x2, x2 from capital X2. Okay. And now what does it mean? It means that since, okay, this is the supremum, and therefore A transposed x1 is less or equal than C for all x1 in capital X1. And since this C is less or equal than infimum of this, and this infimum is of course less or equal than A2 or AT x2 for all x2 from capital X2, okay? And okay, this is exactly what we want for the separation plane. Yes, this means that HAC separates x1 and x2 since x1 is in h less or equal AC and x2 is in h larger or equal AC, and they are done. Okay. Questions?
So
Why
our
are
case
these
were
sets bounded?
Sorry, say it again.
Why these sets are bounded? We can say it from the inequality written, right?
Why these sets are bounded? Yes. Since
Because,
okay, what the
because of the inequality, a times x1 less than equal than a times x2.
exactly. Exactly. You can, this is true for all x1 and all x2. You can take here just some fixed x2, some element from this x2. Of course, you can take some element from x2. x2 is not empty, just take one fixed element. You get here some constant, A transpose times this x2 bar or something like that. And then you see that A transpose x1 is less or equal than this constant. And therefore, this set, which is a subset of R, yes? This is a subset of R, of course, yes? These are just numbers, yes? A transpose times x1 is a number. This set is bounded from above. And for the same logic, this set is bounded from below. Okay? Does it clarify?
Thank you.
You're welcome. Okay.
So
More
our
questions?
case were, so when we had the previous proof with that additional assumptions, we had to additionally prove that X was closed, but in this case we omit that part because of theorem 4, right? Because of the previous theorem.
Exactly. Now they could omit closeness, but they could also omit boundedness, since in the previous lecture they wanted this x1 minus x2 to be closed, and it was not possible to get it just from closeness of x1 and x2, and therefore they assumed in addition that one of them is bounded. But now they have nothing like closeness or boundedness, just two sets, not empty, convex, and empty interior. Okay, but now probably this assumption that the intersection, not empty interior, I'm sorry, that the intersection is empty. Probably this assumption that x1 intersected x2 is empty, this assumption is probably too strong for separation, yes? Remark. The assumption that x1 intersected x2 is empty is probably too strong for separation. What do I mean? Separation. Yes, it is. It can happen that it is possible to separate two sets also if they intersect. Yes. Let's imagine you have this set and this set, and here just one point y, and imagine this is x1, this is x2, and imagine that x1 and x2 are convex, and the intersection is not empty. The intersection is one point. This example. And you can imagine that there is here a separation plane. It separates, our definition, if less or equal or larger or equal, it separates x1 and x2. Okay. Maybe the question is, maybe one can weaken this assumption. Yes, question. Can we weaken the assumption Okay, and if we look at this example, then one could ask a question, probably it is enough just to assume that interior of x1 and interior of x2 has an empty intersection. Yes. Another question one could ask. Is it enough to assume that interior of x1 intersected with interior of x2 is empty to be able to separate two convex sets x1 and x2 by a hyperplane? What do you think? What do you think? Is
Yes.
this the right assumption?
I think yes. From the picture.
From the picture,
I'm-
yes, but from the
I'm
picture,
convinced.
yes, but in general, no. But in general,
So in general,
no.
we can say that.
No. No. The answer here is no. No. And I will give you what we'll do now. I will give you here an example that there you see that it can happen that you have two sets. The interiors does not intersect, and you cannot separate them. And therefore, we will have to replace this assumption by something else. And you will see that the right assumption will be to have here, instead of interior, a relative interior. And with relative interior, it will work, but with interior, not. Okay. Okay, and you see, I give you an example. Very simple example. Just take x1 equal to r2 and x2 equal to the set t0 t in r. Yes, just x2 is just one line. Yes. The second component is 0. Yes. Okay. X1 is the whole R2, and X2 is just this line. Okay. What we see here, the interior of X1, interior of R2 is of course just R2. What is the interior of X2? What is interior of X2? Question to you.
Empty set.
Empty set, and therefore the intersection of interior of x1 and interior of x2 is of course also empty set. Yes, you see, but of course there is no separation between x1 and x2, of course. Yes, since x1 is the whole R2. Okay, therefore, what does it mean? It means that, and again, even if you will take here something different, it will be the same, since the interior of x2 will be empty, and therefore this intersection will be empty, and but no separation. Okay. And now we will see that the right thing to assume, the weakest thing to assume, is that the intersection of a relative interior is empty. Okay, and this is our, let's say, last separation theorem, which says the following, which says that let x1 and x2 be two both in Rn. Yes, x1, x2 both in Rn, be two non-empty convex sets. Again, no closeness or boundedness assumptions. Yes. Then then the following statement holds, that x1 and x2 can be properly separated. I will recall in a moment what does it mean. If and only if the relative interior of x1 intersected with relative interior of x2 is equal to the empty set. Okay. It means, first of all, that this is a good condition. We do not require that x1 intersected with x2 is empty, but we require just the right thing, that the relative interior of x1 intersected with relative interior of x2 is empty. And with this, we get a little bit more than just separation. We get proper separation. I will recall in a moment what does it mean. And you have here really equivalence, and therefore that if the sets can be properly separated, then this must hold. And this means that this is exactly the weakest assumption in this sense. Yes, this assumption for two convex sets which are non-empty is really equivalent to the fact that they can be properly separated. We'll prove it. Okay, and just to recall, what does it mean? What does it mean? It means that there is vector A in Rn and the number B in R and A non-zero, such that A transpose x1 is less or equal than B less or equal than A transpose x2 for all x1 and x1 and x2 and x2. This is just separation. And what is proper separation? And there is at least one element x1, let's call it bar and x1, and x2 bar in x2, such that the inequality between this one and this one is strict one, yes, such that A transposed x1 bar is strictly less than A transposed x2 bar. Okay, which means also that A transpose times x1 bar minus x2 bar is strictly less than 0. Okay, what does it mean? It means more or less the following, that geometrically, that if you take here the hyperplane, this is HAB, as I told you, always the vector A is orthogonal to the hyperplane. Okay, and then we can find such a point x1 bar in x1 and x2 bar in x2, such that the difference between them is not orthogonal to A. Okay, we know, of course, this is less or equal than 0, but we get here strictly less, and therefore this is not orthogonal. It means that you have somewhere here x1 and somewhere here x2. This is the vector between x1 and x2 bar, and this vector x1 2 minus x2 x1 bar minus x2 bar is not orthogonal to A. This means more or less that it cannot happen that the whole set x1 and the whole set x2 are elements of H. Yes, some kind of this kind of separation. Okay, this is proper separation. Questions before we start the proof? Questions? Questions? You were more active in the face-to-face teaching. Okay. Okay. Let me do the proof. Our proof, they have to prove two things, this direction and this direction. They start with this direction. They start that if they are properly separated, then here the relative interior and the relative interior of x2, the intersection of them is empty. Okay, proof in this direction. Okay, the make the proof by contradiction. They assume that relative interior of x1 intersected with relative interior of x2 is not empty. And again, as I told you, in some places it proves they need a kind of idea, but often many steps are just precisely using definitions what we know. What does it mean that the relative interior here is intersected with relative interior of this is not empty. Okay, this means just that there is some point x in the intersection. Okay, in the relative interior of x1 intersected with relative interior of x2. And what does it mean? It means that it is in both, and therefore there is an epsilon larger than 0, such that if you take b epsilon of x intersected with affine whole of x1, this is subset of x1. This means that x is in the relative interior of x1. And since x is also in the relative interior of x2, they have that b epsilon of x intersected with affine whole of x2 is subset of x2. Okay, actually you would get here different epsilons, but you can take the smaller one and then you get just one epsilon. Okay, do you agree?
Yes.
Okay. Now, they are proving in this direction, and therefore they said that they assumed that x1 and x2 are properly separated, and therefore let HAB with A non-zero be separation plane, hyperplane. Separation hyperplane. Okay. What we know that x is in the relative interior of x1 intersected with relative interior of x2. This is, of course, in the intersection of x1 and x2, yes, since relative interior of x1 is, of course, subset of x1, yes. Okay, and now I claim that this x1 intersected with x2 is, of course, a subset of the hyperplane itself. Why? Can you tell me, just in order to see that you are not sleeping? Why is intersection subset of H?
Because if it satisfies both inequalities, then equality must hold.
Exactly. Since if you take, let's say, an element in here, yes, then what you have? Y is in x1, therefore A transpose Y is less or equal than B. Y is in x2, therefore A transpose Y is larger or equal than B. Therefore, A transpose Y is equal to B, and therefore Y is an element in HP. Yes, and therefore they have this. Okay. Okay. What does it mean? It means that our X, which we have taken as an element in this intersection, is, of course, in the hyperplane. And therefore, what we know that A transpose X is equal to B. Okay, first thing we know. What we will show now, we will show we will show that actually x1 is in HAB, and also x2 is subset of HAB. And what does it mean? This means no proper separation. Yes. Since if x1 is subset of the height of a separation plane and x2 is subset of separation plane, then forever you will have here always equality, yes, and here you will have also equality, and also here equality to 0, and therefore you will have no proper separation. This is exactly what we would like to prove, that if we assumed now that this is non-empty, and then we would like to see that if they have here separation, it will be not a proper separation. Okay. Do you understand the general logic?
Yes.
Some other questions? Okay. Oh, here I see it was again something in chat. Let me look. Oh no, it was the same question. Okay, nothing new in the chat. Okay, strange. Okay. We will show that x1 and x2 in this case are subsets of H. How to see this? Okay. This is an interesting argument. Okay, we have. I recall that they have this b epsilon of x, which intersected with affine hull of x1 was subset of x1. Yes. Okay. Now this will be this ball. Yes. Here you have in the middle this x. Okay. And now we consider some point x1 bar in this b epsilon x intersected affine hull of x1, which is not equal to x. Okay, clear? They can take here just some point x1 bar. Okay. And we consider now another point. We just consider it on another side here of x. We consider a point here x1 bar star. How to define it? We consider x1 bar star just by mirroring. Yes, we just mirror here at x. And how to do it precisely? We defined it as x minus x1 bar minus x. Yes. This is, of course, exactly this geometric structure. And if you write it out, what is this? This is 2x minus x1. Okay. You can immediately see that this, what comes out, is an element in b epsilon of x, since it has the same distance to x as x1 bar. Yes, this is the distance less than epsilon. This will be the distance also less than epsilon. And I claim that this is also in affine Hull of x1. Why it is in affine Hull of x1? Can you tell me?
I mean, we change signs in combination, in linear combination, which gives us x1 bar maybe.
Yeah, but what you have here both x1 bar and x are here
Sum
in
is one.
affine Hull.
Sum is one.
And this is an affine combination. Yes, the sum here is 1. And therefore it is also in affine Hull here. Okay. x1 star is here in affine Hull. Okay. Okay. Okay, what we know. We know, let us summarize what we know about these points. We know that x1 bar is in x1. Therefore, A transpose x1 bar is less or equal than B. What's about x1 bar star, this mirrored point? This is, of course, also in x1. Yes, it is even in, it is an element of this, and for this, they know that this is subset of x1. Yes, it is also in x1. And therefore also A transpose x1 bar star is less or equal than B. But at the same time, if we insert the definition, what we get, at the same time, what we get, that A transpose times x1 bar star is what? Is A transposed times 2x minus x1 bar. This is 2A transposed x minus A transposed x1 bar. Okay, here, sorry. Okay, this is true, of course. But let me write it down. We can let it in this way. B. Yes, let us write it in this way. Okay, but we know that this is equal to B, yes, since we said already that X is in the plane, yes. Okay, therefore this is equal, let us continue here, this is equal to 2B minus A transpose x1 bar. Okay, and this is equal to B plus B minus A transpose x1 bar. Yes. Okay. Now, about B minus A transpose x1 bar, we know that this is larger or equal than 0. And therefore, the whole thing will be larger or equal than B. And therefore, what we checked that A transpose x1 bar star is less or equal than B. And A transpose x1 bar star is larger or equal than B. Therefore, A transpose x1 bar star is actually equal to B. Okay? Do you agree? And therefore, x1 bar star, yes?
So previously we already showed that contradiction, right? That no proper separation will exist.
We would like to prove this. This is what we would like to prove. We would like to prove that
so
x1 and x2. Yes, we are formalizing this. Yes, we do not know it so far. Yes, this is just what we want to say. So far, we only know that x is on the hyperplane, this point X. And now we would like to prove that the whole X1 and whole X2 are in the hyperplane, so they have no proper separation. They are trying to prove this. So this is the formal proof. I mean, it is what's intuition behind is it's not so easy to say. Probably you will see now from this proof a little bit intuition, but this is a kind of formal proof that X1 is subset of HAB, and in the same fashion we will see also that also H2 is subset of it. How to see this again? So far what we have shown that X1 bar star is element of HAB. Of course, if you know this, then for the same reason, you will have also, you see that also X1 bar is an element of HAB. Yes, how to see this? Okay, just from this definition, if you know now that A transpose times this is equal to B, then you know that also A transpose times this is equal to B, and therefore A transpose times this difference will be equal to 0. But A transpose by X is again equal to B, okay? In this way you can see it, okay? Let me write it down here in some probably other fashion, since X1 bar is equal to 2X1 bar star minus X. No, 2X minus X1 bar star. And therefore, if you compute A transpose X1 bar, you will get 2A transpose X minus A transpose X1 bar star. It means you will get 2B minus B, and this is just B, okay? Okay, now you have the other, in this situation, you have that X1 and X1 star, and of course also X, all these 3 points are in HAB, okay? And what we actually proved, yes, what we have taken an arbitrary point, X1 bar, in this neighborhood, yes? And in this neighborhood intersected with affine hull of X1. And we have proven that such a point is actually an element of the hyperplane. And therefore we proved that B epsilon X intersected affine hull X1 is subset of HAB. Okay, do you agree?
Yes.
Okay, and of course with exactly the same logic, similar, also B epsilon X intersected affine hull of X2 is also subset of the hyperplane. Now I claim that from this I can say that actually the next step, we claim that actually the whole affine hull of X1 is in HAB, and okay, similar also the whole affine hull of X2 is in HAB. How to see this? It's not difficult. Okay, they have here our ball. Oops, our point X, and imagine, and we know that all points here in the ball intersected with affine hull are in hyperplane. Take now an arbitrary point Y in affine hull of X1. Okay, what we do, we consider here the connection line. Okay, they say, okay, let y be in affine whole of x1. We consider xt, which is 1 over tx plus ty. And of course, this xt is an element of the affine whole of x1. Yes, this is an affine combination. X is an affine whole, y is an affine whole, xt is an affine whole. Sure. For t equal to 0, we get x0 is just x. And it is in hyperplane. Now for t1 small, to take it smaller than epsilon times something, choosing small, what we get, what we will get that this xt1 will be in b epsilon, and of course it will stay in affine whole of x1. Yes, as said here, and therefore it will be in HAB. Okay. But now if you have, this is, I don't know here, this point xt1. But now, of course, you know, if you have 2 points, if you have here 2 points which are in HAB, in the hyperplane, then of course a connection line, the whole line between these 2 points, is in the hyperplane, just by definition of the hyperplane. Yes. Therefore, the whole line through x0 and xt1 is in the hyperplane. Okay, and therefore also y is in this hyperplane. Okay, do you agree?
So we found another point in this neighborhood that is also in hyperplane, and we say that entire line will be in the hyperplane.
Exactly. Since if 2 points are in the hyperplane, then of course the line going through these points is in the hyperplane, since hyperplane by the definition of the hyperplane. Okay. But now from this, if you know that the affine whole is in H of AB, then of course also x1 itself is in HB, since x1 is a subset of its affine whole. Therefore, we get that x1 is in the hyperplane and x2 is in the hyperplane. And therefore they have no proper separation. Since if you take now x1 in x1, we know then x1 is in the hyperplane, and therefore A transpose x1 is equal to B. Similar, if x2 is in x2, x2 is in the hyperplane, and therefore A transpose x2 is in B, and therefore A transpose x1 minus x2 is 0 for all such x1 and x2. And therefore no proper separation, and we completed the proof. We completed the proof in one direction, that if there is a proper separation, then the intersection of relative interiors will be empty. And after break, we will prove other way around, which is actually, I don't know, more important for applications, that if we have that the intersection of relative interiors of two convex sets is empty, then there is a proper separation. But this will be done after break. Let us make a break of 10 minutes approximately and then continue. Okay? Okay, see you in 10 minutes.